Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 44, and it is entitled Pendulums and Advanced Kinematics. This lesson is in two parts. Your authors have seen fit to put two subjects together in the same lesson that have very little to do with each other, and we'll take them one at a time. We'll begin with the pendulum. I have a story to tell you. It's one actually that's told by David Goodstein in the series from Caltech entitled The Mechanical Universe. I'm not sure that it's true, but it's a good story, so I'm going to tell it to you anyway. It's about our old friend Galileo. When Galileo was a young man in Pisa, he attended Mass at Duomo. That's the magnificent cathedral in Pisa, whose bell tower is the famous Leaning Tower of Pisa that you can see in this image over here. In Duomo, there's a lamp that hangs down from the ceiling by a long cable, and it's pictured in this image here. On this particular day, the lamp was swinging back and forth. Probably it had just been lighted. And Galileo, being Galileo, noticed something about the swinging lamp that no one had ever noticed before. And I'm going to try to demonstrate it to you here. He noticed that each complete swing of the lamp took exactly the same amount of time. When he first started swinging the lamp, and it had a large arc, it moved quickly through the bottom of the arc. But later on, when the swinging had died down some, and the arc was smaller, it swung more slowly through the bottom of the arc. But the total amount of time for each complete swing was always exactly the same. How did he determine that? Well, he timed the swings by counting his own pulse. I've often wondered about that, having realized that he was making a great discovery why his pulse didn't start racing and ruining his own measurement. But in any case, he timed it using his own pulse. Now I figured that each complete swing of that lamp must have taken 5 or 6 seconds, and he had to watch it go through many, many complete cycles as the motion got smaller and smaller, counting his pulse each time to make sure that each swing took the same amount of time. It must have been a very dull sermon. The lamp is still there in Duomo, Pisa. It's called Galileos Lamp, and for a few hundred lire, you can buy a picture of it from the enterprising street vendors outside the piazza. The only thing wrong with this story is that, according to the church records, the lamp wasn't actually installed until 10 years after Galileo died. But Galileo really did make that discovery, and it was extremely important because what he had discovered was that a pendulum could be used as a timing element. And in fact, his discovery led him immediately and directly to the invention of the first accurate clocks. The kind of motion he was studying is called simple harmonic motion, a lesson that we have covered in a previous time, and the subject that occupies us today is the simple pendulum. Let's define what a simple pendulum is and what are some of the important aspects that we have to be cognizant of as we look at the pendulum. A simple pendulum is a point mass that's suspended from a massless string. It turns out that the simple pendulum doesn't execute exactly simple harmonic motion unless the amount of the angle from which it is displaced from equilibrium is less than about 10 degrees. Let's sketch what we mean by that. I've sketched here a point mass, M, at the end of a string that has a length L, and this particular pendulum is displaced away from its resting position or equilibrium position by some angle theta. Now there are all sorts of things that I could take a look at here. For instance, I could talk about the fact that the pendulum is moving through a circular arc and that there's going to be centripetal acceleration in addition to tangential acceleration. We could talk about the gravitational potential energy that the pendulum has when it's pulled away from equilibrium and how it converts that into kinetic energy when it's down at the bottom of the swing. We could talk about the maximum amplitude of displacement when the thing is pulled to the side. And in fact, all of those things are going to be important in time. What I want to focus on today, though, is how long it takes for the pendulum to go through one complete arc, and we'll refer to that as the period of the pendulum. I'm going to write down a formula here that comes from the solution to a differential equation that we're not going to solve here, so you'll just have to take my word for it. But this formula for the period of a simple pendulum is very important. Here it is. The period for a simple pendulum, the time it takes for one complete cycle, is equal to 2 pi times the square root of the length divided by the acceleration due to gravity, g. It turns out that the period of this pendulum will be the same no matter what the mass is of the object. You see that mass doesn't show up in the period formula. And you can also see that it doesn't depend on how large the swing is, what the amplitude of the swing is. Now, it is true also that a pendulum only approximates simple harmonic motion if the angle of displacement is less than about 10 degrees. You'll hear some physicists talk about the small angle approximation for the period of the simple pendulum. This period that's written down is a small angle approximation. And that's the only kind of thing that you're going to see on the AP exam. So we're talking about the swings of pendulums whose amplitude is fairly small. You may also recall that the frequency, the number of vibrations or oscillations per second, is the inverse of the period. And so for a simple pendulum, you'll take the reciprocal of this equation for the frequency. With these equations in mind, let's solve some numerical problems for the simple pendulum. Example 44.2. The length of a simple pendulum is 0.86 meters. The local attraction of gravity is 9.81 newtons per kilogram, and the mass of the pendulum bob is 0.063 kilograms. By the way, the bob of the pendulum is the mass that's at the end of the string. What is the period and what is the frequency of the pendulum? To answer this question, we pull out our period and frequency formulas and put in the numbers. There are more red herrings given in this problem, more numbers that we are given than we actually need to solve the problem. So let me take the length, 0.86 meters, and the acceleration due to gravity, which your authors, I think, have kind of tried to disguise as the attraction of gravity. 9.81 is what we're going to use instead of 10, and we're going to substitute those numbers in. And now I'll substitute them into my calculator, and I get that the amount of time for one complete oscillation, one back and forth motion, takes 1.86 seconds. The frequency is going to be the inverse of this, so I'm going to take the reciprocal of this number. When I put this into my calculator, and I'm hanging on to all the decimal places that came from the earlier calculation, I get 0.54 hertz for the frequency. In other words, a half of an oscillation, a little more than half of an oscillation per second. In future lessons, we're going to have to deal with some geometry of the pendulum in order to talk about conservation of energy. And as we get to those, we'll try to sort out what the geometry is. For the pendulum lesson, we are finished. We're going to move on now to advanced kinematics.